Hello, let's do a walkthrough solution of the mid-level challenges. I'll try and illustrate kind of some of the ideas that I'm having as I'm doing them and what I think good practices might be. So this first method is detect a 3x5 rectangle which all contain the same value. So a lot of groups had the following idea. They said, let's loop over all the locations, and then from each starting location, loop over a sub-array that goes down by 3 and over by 5, checking if all the values are the same. So let's go ahead and do that. I'm going to call this, did I give you a method name? No, I didn't. Okay, so let's call this detect equal subgrid or subarray, and I'll give it an array. I guess let's create a test array. I'm not going to work that hard creating a test array because I actually already have an idea that I like better here. So actually what am I trying to do? 1, 2, 3, 4, 5. So let's make each row 6 long. So one thing that you might notice is I start by making my test, and it's not a very good test. But I think this is kind of like a nice organized way to begin. So I'm going to detect equal subarrays in this array. Let's print out what the output's going to be. Hopefully this output will be true. All right, so we're looping over all the rows and all the columns. And then what a lot of people were doing were they were starting here to make 2 more nested loops. So like row check starts at the row, and then row check is going to go up to the row plus 3. So it's like we're going to be, like for each row and column, we're going to be looping starting at the particular row and then going down 3 rows and so on. And so you could have some nested loops here, but some people remembered that I'd said that having multiple levels of nesting is often bad style. So it seems appropriate to break out a helper method here. And what the helper method does is it checks for an equal subarray. So is equal subarray, where I'll give it my array and I'll give it the row and column that I want to start at. And it will check to see, starting at this place, is there a 3x5 subarray that are all equal? And so if it finds an equal subarray, I can return true right away. Otherwise, I'll keep looking, and then at the end, I'll return false. Great, so now my method works if only I had this method. So let's go ahead and make it. So now here I'll have here, let's call this start row start column so that way I can name this one row. So my row is going to start at the starting row, and it's going to go up to the starting row plus 3. And then, let's do, so then for I column starts at the starting column and goes up to starting column plus 5. Well, it's got to be less than that. And so now I want to check to see. So again, some people were thinking, all right, I want to see if they're all the same. So let's do this. Let's make a counter, and we'll say, we'll count how many are the same. So we'll say if array RC equals array starting row starting column. Then let's add to the counter. And then at the end, we'll see, is the counter equal to the number of unique locations? That would work, but it's a little bit more efficient to just check for, are they ever not equal? Because if they're not equal, we can immediately return false. Otherwise, we'll return true. All right, so that's looking pretty good now. So now I think my method should be done, in a crisp 4 minutes, 27 seconds. I guess let's run it, but this isn't like a terribly good test case, but at least we'll see if we're going out of bounds or anything. Oh, are we going out of bounds? We should be. Oh, except that we're exiting so fast. Well, let's let ourselves run. No, I guess let's fix it. So So the reason I said we should be is because up here we're looping over all rows and columns, and then we're looping down and right from there. So let's pretend we make it all the way to the bottom row. And then we say, is there an equal subarray starting at the bottom row? Well, we're going to start at the bottom row and loop down, and that should be taking us out of bounds. And the reason that we're not actually getting an out of bounds exception is because we find a subarray like right away at the very beginning. But what we'd want to do here is restrict the range of rows that we can visit. So because we're going to be going down by 3, we want to stop 3 before the bottom. And because we're going to be going right by 5, we want to stop 5 before the right-hand side. So now that's kind of controlled that. So this, as I was saying before, like this test case isn't a particularly good test case. I would really like to generate some more convenient test cases. So let's spend about 5 minutes doing that. So I'm going to have a make array where I give it the size of my array. Let's give it a 10 by 10 array, and I'll initialize it. No, let's just do that. Let's initialize it to random values. So make random array. And you might be thinking that's not that helpful yet. So this is height. Let's call this rows and calls. So int bracket bracket array equals new int rows calls. And then let's loop over all the things. So then array row rc equals int math.random times 1,000. Let's actually make this called max. I think it's just good to make it as general as possible. Well, strictly speaking, that's not true. I thought that was a nice thing to generalize. All right, so we should be making a random array. Let's go ahead and make a method where we can actually like print out our array, because we're going to want to be able to like see what it looks like. So test length, and then column test 0.length, except I shouldn't have called it test. I should have called it something else. So let's do, what can I do? F6? Yeah. So let's call it R. And now we'll print array RC and then a space. And then at the end of the row, we'll have a print line. Great. So let's just make sure we're getting some random arrays now. Great, we're getting some random arrays. So now, but like that's not going to help us because we need to detect 3 by 5 subarrays. So now I want to do like add rectangle to an existing array where I tell it the starting location. So let's start at like 3, 4. I want to give it the height and the width, and then I want to give it the value. And so you'll see what this is going to do in a second. So here's my array. This is starting row. This is starting column. This is height. This is width. And this is value. So this is going to be very much like the code for checking the subarray. In fact, let's just copy that. Except instead of, wait, what? Oh, here, this part. Except instead of checking things, we're going to be assigning values. So here I'm starting at the starting row, except I'm going down by height, and I'm going right by width. And then instead of an if statement, I'm saying array rc equals val. And then I don't need to return anything because we're being passed a reference to the two-dimensional array. So any changes we make inside the method are going to get permanently reflected in the array. Okay, so let's go ahead and see did we actually add a rectangle at 3, 4, whose height is 3 by 5 and whose value is -4. Great, so now we see it there. And so now we can go ahead. So let's comment this out and see if we're going to detect an equal subarray, and we should not. Was that 5 minutes? Like I said, yeah, it totally was. Okay, so it should say false because there is no 3 by 5 subarray. But now if we uncomment this, Now it should say true because we have found a 3 by 5 array. Okay, was this the best set of test cases ever? No. Maybe we could be off by 1. So like I should maybe make a test case where the 3 by 5 rectangle is like right up against an edge, like the right edge or the bottom edge. Maybe I should test to see if it falsely detects a 2 by 5 or a 3 by 4 rectangle. So there's a bunch of edge cases I might want to test for. But I think for the purpose of this video, that's what I wanted to bring out. So 2 big ideas here. One big idea is don't be so focused on the problem that you're solving that you don't take 5 minutes to make it easy for yourself to generate useful test cases. Sometimes that investment of like making code to write your test cases can really pay off in the end if you need to debug. Certainly it helps you like think more clearly through what's happening. Another big idea was this idea of using a helper method rather than having a whole bunch of nested levels. If we wanted to, we could actually generalize this quite easily the way that we've written it. Instead of 3 and 5 here, we could pass in a height and a width. And so then this would be height and this would be width. And then we'd also need to pass that into is equal subarrays. So int height, int width. And then we'd be going here height and width. So that was like less than 1 minute, but now I've generalized it so that we can detect not just 3 by 5 arrays, but subarrays of any size. Okay, let's try and hammer these out kind of fast. So perimeter sum will hopefully be pretty fast. So s out perim sum, where we'll give it the test array. Again, I'm programming by intention. This should not be going too fast. It should not be Boolean. It should be int, and I'm going to call this array because that's a better name. So for the perimeter sum, let's see. We could do this. Let's loop over all the rows, starting at 0, going to the last row. And so if I'm looping over all the rows, let's add up like all the values in the leftmost column. So int sum equals 0. So I could say sum plus equals array visit all the rows, but only column 0. So now this is looping down the left-hand side. If I wanted to, I could have another for loop that does that same thing, except we're doing all the rows on the rightmost column. So what is the rightmost column? It's array r.length minus 1. Okay, but then something to notice here is it's a little bit inefficient to have 2 different loops that both loop over the same set of values. Why not just add both of these in the same for loop? So here I'm looping over all the rows and I'm adding both the left and the right. And then I could do that same thing, except let's do all the columns. And in both cases, I'm going to have the column index be the ones changing, and we'll do row 0, which is looping across the top, looping across all the columns in the top row. And then here, array.length minus 1. So looping across all the columns in the bottom row. Okay, so we might think that this is good if we hadn't made a test case. There's a very subtle problem here, which is we're actually double counting all the corners, because we hit all 4 corners once in this loop and once in this loop. So one easy fix would be let's just start from column 1 and end right before the last column. So now we're only hitting the corners in the first for loop, and here we're not visiting any of the corner values. A different thing that we could do would be, like, let's just let it add all the corners twice, and let's subtract all the corners. So we're going to subtract 0, 0 plus 0 array length minus 1. So I already don't like this way because it's more typing. But you can see, like, if we've double added all the corners, we could subtract them all once, and now we've only counted them all once. Let's go back to the other thing that I had a second ago. All right, cool. In order to make this reasonable, let's do this. Let's do a 3 by 3 whose size is 3. Let's run it. Okay, so the perimeter is 2, 4, 6, 8, and then here it says 8. Cool, looks good. All right, what now? Find lower right. So the idea is we are guaranteed, so we're given a grid and we're given a starting row and column. And if the starting row and column contains 0, then we immediately exit with 0. Otherwise, we find the lower right-hand corner of the rectangular region that we're in that contains all the same value. And it's guaranteed that all the non-zero values are these kind of separate rectangular regions. Okay, so how are we going to do that? Let's get the easy part out of the way first. So let's call this... Here, let's comment these out. Let's call this find lower right. We'll give it test, and we'll give it a starting location. We'll create the method signature. Array, this is row, this is call, except we're going to return a location object. Let's go ahead and make our location object right now. It might feel like a pain to do, but look at how fast it's going to be. Location... private int row call, and then I can even generate the constructor, auto generate, and if I want to, I can say getter setters. So like it was less than a minute to make our own class here. So let's, like I said, let's do the easy part first. So if so there's all kinds of safety checks you could do. So you could say like, if array equals null, then return null. If we'd want to check for inbounds. So if row is less than 0 or row is greater than or equal to array.length, or column is less than 0, or column is greater than array 0.length, then we'll return null because it's an invalid starting location. If none of that is the case, then we can check if the starting location contains 0. So if array row call equals 0, then we return 0. Oh, wait, does it say return 0? What does it say? No, it says return null. Okay. Great. So those are all the easy to check things. If we pass all those checks, what are we sure of? We're sure that we have a valid starting location and that the starting location contains a non-zero value. So conceptually, I think what might be nice is let's actually have a while loop where we keep looking down until we find the end of what we're looking for. So we'll say while, let's create a new, well, do we need to? No, I guess we don't. So while array row call equals, let's get our starting value. So int val equals array row call. All right, so we'll store the starting value, and then we'll say as long as we're still looking at a number that's equal to the starting value, let's go down. Let's add to the row. So that will keep going down until eventually these aren't equal anymore. And as soon as they're not equal, we know we are one past the place we want to be. So let's do row minus minus because we're one row below the bottom of rectangle. And so now we can do that same thing for the column. So we'll say column plus plus. And then we'll say column minus minus because we're one column to the right of the rectangle edge. And then we would say return new location row call. Okay, so in theory this is going to work. There's one bug here, which is what happens if we, like, this is our starting location. We're going to keep going down finding 7s until eventually we're off the grid. That wouldn't happen if we got placed down here, because here we'd go down, aha, 0 is not the same as 2, and so we'd say it must be this column that's right, it must be this row that's right above us. But here we hit the edge first. So let's add a test. Let's say if it's still equal to the value and row is inbounds, so row is smaller than array.length. So you might think that this is working, but the problem here, IntelliJ knows it, row less than array.length is always true when reached. So the issue here is that, let's say row gets too big. If row is too big, we actually first check the value before we check if it's too big. So this would actually go out of bounds before we have a chance to check to see whether it's valid. So the way you fix this is, let's reverse the ordering. So here. So as long as the row is in bounds and we contain the value we want, let's add to the row. So this is going to fail, or we're going to exit the loop either if we see a value that's not the one we want, or if we go out of bounds. And in either case, we still want to subtract 1. Because if we go out of bounds, then it must be that the last row was that bottom row. And so we need to subtract 1 in order to get there. So same thing here. As long as column is less than array row length and. So as long as the column is in bounds, etc. Okay, cool. So that all looks good. What now? Let's do, that was find lower right. Okay, transpose. Awesome. So let's look at what's happening with this transposition. It looks like here in the source array, if we're sort of starting in the top left moving right, in the target array that's starting in the top left moving down. If you put it differently, it sort of looks like we've sort of flip-flopped this along the diagonal. Put differently, it's like we've reversed the rows and columns. So here this number 2 is at row 0, column 1, and here it ends up at row 1, column 0. So that seems easy enough to do. Let's try and do it. So transpose the test array. Okay, so we don't want Boolean. Let's return a new int array, and you'll see why in a minute. All right, so let's do this. Let's create our new int array. What am I trying to do? I'm trying to say array equals new int. So let's do array.length, array 0.length. So now, oh, I can't call them both array. Let's call this out. Okay, so let's loop over all the rows like we do, all the columns like we do, except in the output. So we're going to have like output something equals array row call. And the answer is we're going to assign this value to the place where the rows and columns are reversed. So we're going to use column as the row and a row as the column, and that should work. And then we'll return out. Okay, so this should work. The only time that this is going to fail, well, okay, let's go ahead and test it. So I've got a 3x3. Let's make this 10. We'll print it, and then we'll also print the result of transposing it. Oh, this is not going to, there's a reason why we wrote our own print statement. All right, here we go, and then let's put a line of dashes in between. All right, so we've got here, and then it looks like, yeah, it does look like it's been transposed. Here's the problem. What if we make a 6x3 array? Let's run that. Now we get index out of bounds. And the reason why it's out of bounds, oh, I hope I haven't been typing off the edge here where you can't see. Oh dear. The reason it's out of bounds is because where did I go? Okay, the reason it's out of bounds is because the new array dimensions should also reflect that transposition. So if I'm swapping rows and columns, I also want to swap the height and the width. And so that's the last change I'd need to make. So now I should be able to run it again. Cool, and here we do see, here it was tall and narrow, and here it is short and wide. Okay, I hope that this has been helpful.